Great, thank you, Koen. I guess we're off to a great start. So what I wanted to do, I guess in the next 20 minutes or so, is tell you about a new tool. It's called an exponential verifiable random function, an eVRF. And it's a tool that's useful for protecting secret information in a blockchain environment. So hopefully this will be useful to you. We'll see how it goes. And I should say that this is joint work with Iftach Heitner and Yehuda Lindell. Okay, so let's start at the beginning. What is multi-party signing and decryption? So I imagine many of you know this, but let's just make sure we're all on the same page. So the goal is basically to protect a secret key by splitting it, right? This is a very common thing to do. For example, in the context of public key encryption, you might imagine somebody encrypts a message to a public key PK, and the question is, how do we decrypt it? Well, the way we would decrypt it, the way we would protect the decryption key is we split it up into 3 pieces in this case. And basically, each one of the pieces will be used to create what's called a decryption share. And those decryption shares put together will be able to decrypt the entire message. Okay, so the point would be that decryption is only possible if all the participants agree to decrypt. And the point is, if one of these secret keys is stolen by the adversary, maybe even 2 of the secret keys are stolen by the adversary, that doesn't give the adversary anything because all 3 are needed in order to decrypt. The same thing also applies on the signature side. So again, we have a public verification key. And the question is, who can sign a message M? And again, the way we can protect a signing key is by splitting it up into pieces and have a signature is generated only if all the participants actually agree to generate a signature. Again, if 1 or 2 of the shares is stolen, the attacker is not able to generate a fake signature. Okay, so this is sometimes called threshold cryptography, although I like the term multi-party signing and decryption because in this, as I described it here, there's no threshold. Yeah, all participants are needed to decrypt, all participants are needed to sign. Now, of course, as we said, there's also a threshold version of this when only, let's say, 2 out of 3 participants are needed. So you can see in this case, 2 of the arrows disappeared on the bottom, and only in this case, only 2 parties were needed to decrypt, or only 2 of the 3 parties are needed to sign. Okay, so this is something that I imagine many of you are familiar with. It's a very common thing in the blockchain space to protect the key by splitting it into shares. In some cases, maybe we even put these shares inside of an enclave to further protect the shares themselves, but that's sort of an added security that we can do. The basic idea is to protect the key by splitting it up. Okay, so the question is then, where did these shares come from? Yeah, how do we generate the shares to begin with? And here there are 3 ways to do it that I wanted to mention. Yeah, so the first one is what's called a trusted setup. Yeah, so basically we have this angel in the sky that just runs around and generates the secret keys for us. So it generates the secret key shares, it generates the public key for people to encrypt or to verify signatures with. And then once the trusted setup is done, basically the angel in the sky disappears and we have our secret key shares. Yeah, of course, the trusted setup will know what the global secret key is, so that is kind of important for it to actually disappear and never reveal what the secret keys are. So a better way to do it, one that doesn't require a trusted setup, is to use what's called a distributed key generation, or a DKG, distributed key generation. The idea is that the parties sort of talk amongst themselves, they implement a multi-party computation protocol, and the secret keys just appear, and now the secret keys appear to the parties, and the public key is published to the world. So that's a second way to do it. And a third way to do it, which might be a little bit less familiar to you, is using what's called local key generation. And with local key generation, what happens is each party, there's no protocol, each party just locally generates a secret key, publishes the corresponding public key, and now you can imagine when you want to decrypt or verify a signature, you might actually need all 3 public keys in order to do it. Yeah, so again, the key is split, but in some sense the public key is as big as the number of shares. So it sounds like this third approach is actually no good because it results in fairly large public keys, right? The number of public keys is basically proportional to the number of users. But it turns out, this is actually a good thing to know, that we actually have very good signature systems, for example, that even if you do local key generation, we can take all the public keys that come out of local key generation and compress them into a single short key. Okay, so I want you to remember that in fact local key generation is actually quite practical. We can take a bunch of public keys, compress them into a single public key, and that way have very simple key generation using still a very short public key. All right, so far so good. So yeah, so what I want to do next is basically, actually I guess I should just talk a little bit about the fact that multi-party cryptography is actually quite useful. Again, many of you know that multi-party signing is used to protect asset keys on a blockchain. It's used for governance keys. It's used for consensus keys and so on. So very, very heavily used. What's interesting is now we're starting to even see multi-party decryption being used in the blockchain space, particularly for encrypted mempools. So I hope many of you have heard of encrypted mempools, where the idea is that a block remains encrypted until the moment that it's finalized on chain. Yeah, at the moment that it's finalized, it's decrypted, and this is a method this is kind of a technique that's used to make it harder to do sandwich attacks and other MEV-like techniques. Yeah, so both multi-party signing and multi-party decryption is getting actually quite a bit of use in the blockchain space. Now, it turns out, because of this, even though this area, multi-party signing, multi-party decryption, this is like a 30-year-old area. This is not a new problem. For 30 years, there have been papers written on this topic. It turns out the blockchain space actually raises lots and lots and lots of new questions and lots of new challenges in the space. Yeah, and this is what I wanted to talk about today. Yeah, so let's talk about a specific issue, and I want to show you basically one way to generate a shared key using a very efficient protocol. Okay. So now we're going to get a little bit more technical, but this is still going to be a fairly high-level talk. So if anybody's interested in the details, come see me after the fact, and I'm happy to go into more details. Okay, so how do we generate a shared key? So let's think about the traditional signing scheme like Schnorr signatures or ECDSA. In Schnorr signatures or in ECDSA, the secret key looks like a random number alpha. It's a random number alpha between some number 1 and q. And the public key, roughly speaking, is G to the alpha, where G is a generator of some group. Yeah, so basically it doesn't matter if you don't even know what a cyclic group is. All you need to know here is that the public key is basically an exponentiation of the secret key. Okay, so now the question is, how do we generate a shared key? Yeah, we'd like to sort of jointly generate a shared secret key without a trusted party. And the key should be uniform, should be random, as long as one of the parties generating the key is honest. And so the question is, how do we do that? So here's a really simple way that, maybe the first thing that comes to mind when you want to generate a secret key, a shared secret key, and unfortunately this method actually doesn't work. So let me show you the method, and you guys will see right away why it doesn't work. So the natural thing to do is basically have each one of our participants sample by itself a random number between 1 and q, so alpha 1, alpha 2, up to alpha n, and then what they'll do is they'll publish g to the alpha 1, g to the alpha 2, g alpha n, and so on and so forth. And then we can aggregate all these public keys that they all publish and just multiply them out. Yeah, and then we'll get our global public key to be g to the sum of the alpha i's. So you can see the secret keys are going to be the alpha i's, and we have one public key, which is basically g to the power of the sum of all the alpha i's. So this is a very natural way to generate a public key. Unfortunately, this is completely insecure. Completely insecure. You should never, ever, ever do this. So why is this insecure? Here's like maybe I could pause and see if anybody can come up with it with the attack, but let me actually just show you the attack. The problem is that the last person, Zoe, actually has a lot of power here. Right? So what Zoe can do is actually cheat, and instead of publishing g to the alpha n, what Zoe can do is wait for everybody else to publish their public values, and then publish g to the alpha n divided by everybody's public values. Now look what happens when we multiply all the shares that were public, right? The protocol says multiply all the public values from all the participants. When we multiply them all out, you notice that the contributions from the first n-1 parties, they cancel out, and we're left with a public key being equal to g to the alpha n, which means that now Zoe knows the secret key, which is actually not what we wanted. We wanted the secret key to be shared among all the participants, and in this protocol, with this broken protocol here, we can end up in a situation where Zoe knows the secret key, so this is not a shared key. Zoe knows everything. All right, so this is absolutely the wrong way to generate a shared secret key. So what do we do? So again, there's a standard solution to this problem. The standard solution is what we call it's a two-round protocol, what we call commit then reveal, where basically we force all the participants to commit to their alpha i's or commit to their G to the alpha i's. And then later on, so once they've all committed, now they can't change their mind anymore. And so later on, they reveal what their committed values are, and we take the product. Yeah, so this is a standard, very standard technique for generating this shared exponent using a two-round commit and reveal. But the question we were wondering about is, can we still have a single-round solution? Yeah, two-round protocols are much harder to deploy in the real world. The question is, can we have a single-round solution? By the way, I should stop here and say that this problem of generating a shared alpha and a public G to the alpha, this is not just used for key generation, this is also used for signing. Yeah, and so this question also comes up in the context of signing, and typically in signing protocols, people use commit and reveal, and that's actually why we end up with a multi-round protocol. Okay, so the question is there a single round protocol that does the same thing? And so the way we do it is it's based on an observation that says that if you look at what Zoe knows here, Zoe under this attack actually doesn't know the discrete log of her own public value, right? She can publish the public value, but she does not know what the discrete log base G is of the value that she published. Yeah, because it includes everybody else's public values. So that might give you an idea. How would we prevent her from doing the attack? Well, what we can do is we can force everybody to also publish a zero-knowledge proof that they know the discrete log of the value that they published. In the attack that I showed you, Zoe doesn't know this discrete log, so she won't be able to produce a valid proof, and as a result, she can't do the attack that I just mentioned. Okay, so you can see the single-round solution is a very simple way to make sure that that Zoe would not know the results because she does not know the discrete log in the case of the attack. Unfortunately, this protocol is still insecure. This is still insecure. So what is the attack now? The problem here is that Zoe actually doesn't know, Zoe can't know the actual secret output, but because she's the last one to go through the protocol, she's the last one to actually publish a value, she can bias the final public key. Yeah, she can just try a whole bunch of alphas. Rather, she can try a whole bunch of alpha n's until the resulting public key comes out to be the one that she wants. Yeah, and it turns out maybe in the distributed key generation protocol, a biased public key, it's not great, but maybe it's not as problematic. In the context of a signature protocol, a biased randomness will destroy the protocol. Yeah, will make the protocol completely insecure. All right, so the problem is, even though this looks like a solution that's quite reasonable, it actually doesn't work because the last party can still bias the output. So what do we do? Okay, this was kind of the starting point. Everything I said up until now is kind of classic. This was the starting point of our work. So the question is, can we somehow still have a one-round protocol where the final output is completely random and not under the control of any of the parties? So let me show you how to do it. So the new primitive that makes this possible is an abstraction. It's called an exponential verifiable random function. Yeah, an eVRF. It's kind of a very neat primitive. Turns out it has a lot of applications, including key generation, distributed key generation, and distributed signing. But here we'll just focus on distributed key generation. Okay. So the idea of an exponential VRF, exponent verifiable random function, is to basically prevent the bias by basically removing any choice that the participants have. Yeah, they can't choose their randomness. Their randomness is going to be pre-specified to them. As the result, they can't do the bias attack. So let me explain to you what is an eVRF. An eVRF is actually a very simple mechanism. So what it does is it has a key generation phase where the parties will generate a secret key for themselves and a verification key that's going to become public. So every party, each one of the n parties, will run this key generation procedure. It also has an evaluation algorithm. The evaluation algorithm basically will take the secret key in an input X, and then it will output a random value alpha, or I should say a pseudo-random value alpha, along with the exponentiation of alpha. So y here is g to the alpha, and along with some proof pi. So what will actually become public is the value y, the value g to the alpha. The value alpha is going to remain secret only to the participant, and what the proof will do is the proof will actually prove that the value y was computed correctly. In other words, if you compute the logarithm of y, you really get the pseudo-random alpha. Okay, so that's what the proof does. And then there's a verification algorithm that takes x, y, and pi and accepts or rejects. You notice the verification algorithm doesn't know what alpha is. All it sees is y and pi. Okay, so that's it. That's an eVRF. Again, there's a formal definition that goes with all this, but I won't go into that here. So again, the point of an eVRF is you get a random value, but the random value is only available to you in the exponent. Okay, so why is this useful? The cool thing about this is if we wanted to do key generation now, effectively, this kind of solves the problem. Yeah, it solves the problem, and let me show you why. The reason this works is, or the way we would generate keys using an eVRF is the following. First of all, we're going to make every party generate an eVRF public key. Yeah, so every party will commit to VK1, VK2, VK3, and so on. And they do that at the beginning of time. This is a one-time setup. They never have to do this again. And of course, internally, they have the corresponding secret key for the eVRF. So I should say, by the way, this sets it up for many, many evaluations, for many possible DKGs, not just for one. So you commit once, and now you can run the DKG protocol as many times as you want to generate many shared keys. So now later, so you've done this setup, one-time setup, and now you want to generate a shared key. What happens is all the parties sort of agree on the name of the key. Let's say I chose Panda, but you can imagine maybe you use Uniswap or whatever name you like to give to the shared key. They all agree on the name of the shared key. And now they use the eVRF basically to derive alpha 1 to alpha n. You notice they use the eVRF to derive these alpha 1, alpha 2, up to alpha n. They don't choose them themselves. They are sort of forced to use a particular alpha. Yeah, they're committed to their alphas because of the eVRF mechanism. Yeah, so they don't sample them, they compute them. And what they publish basically are the g to the alphas and the exponent, along with a proof that this is a correct evaluation of the eVRF, right? Now, everybody can verify that these values, these yi's, really are consistent with the eVRF, and now we define the public key as the product of all the yi's. So this sort of eliminates all the attacks that we talked about so far, because there is no choice for the participants. Their complete participation in every DKG from now on until the end of time is completely dictated by the public key that they committed to at the beginning of time. In some sense, this is a commit and reveal protocol, but the commit phase only runs once. Yeah, and then you can participate in as many DKGs as you want. Yeah, and the same thing in the case of a signing protocol. You commit once to your eVRF key, and now you can participate in as many signing protocols as you want, and your random contribution is basically forced. You don't have a choice in how to, in what to contribute, and because of that, all the attacks go away. So anyhow, I wanted to share, it's kind of a cute abstraction. It's a very simple mechanism to understand, and it's actually quite a powerful tool. So I wanted to kind of make sure you guys are aware that this exists, and it's quite practical and ready to be used. So I did want to show you a little bit about how to build an eVRF. In the paper, we give a couple of constructions for how to build an eVRF, but I think in the interest of time, maybe I'll skip this and come see me if you want to see how this works. And so let me kind of jump to my last slide, which basically says that the blockchain space is an amazing time for cryptography, because the blockchain space generates so many new problems to think about. In particular, multi-party signing, multi-party encryption. It's a 30-year-old area, but because of the application in blockchains, all of a sudden there are lots of new questions to think about, lots of new requirements, and lots of new opportunities to work on new problems. And so, it's really fun to think about these problems. And maybe I'll plug one of our talks at the main conference, the SBC conference, about how to deal with misbehavior in the context of multi-party cryptography, when some of the parties might reveal their secret keys to somebody who pays for it. And the question is, how do we prevent people from selling their secret key shares so that they're held accountable if they ever do that? Yeah, so that will be one of the talks at SBC. Anyhow, if you guys are using multi-party signing, multi-party encryption in your projects, come talk to us. There's lots of new developments in the space that I would love to share with you. And with that, I'll stop, and thank you very much. All right.